Good afternoon, all. Welcome to today's GWatch webinar. My name is Rajan, Vice President Sales and Commercial at GWatch, and it's a pleasure to have you all today. Today's webinar is focused on the introduction of 4D gravity and subsidence monitoring technology, with the aim to discuss the key applications that can help our customers to improve subsurface understanding and reduce the field development costs. During this unprecedented COVID-19 period, most of our customers continue working from home and most of the industry events have been delayed. This webinar forms part of our digital strategy to continue engaging our customers and share the latest technology updates. There is a full schedule of upcoming digital events available on our website, octio.com. Just some general comments about today's webinar. We aim to have this webinar for 45 minutes. Out of that, we'll spend 25 minutes or so for presentation, followed by 15 to 20 minutes for Q&A. I would like to highlight, as today's session is mainly focused on technology introduction, we have a follow-up webinar coming on 10th of November, where we'll go into detailed technology discussion and also review the recent case studies. Again, a full list of events is available on our website, octio.com. We'd love to have some feedback and questions from your side. Please type your questions in the chat box or the Q&A button available with the webinar, and we aim to go through as many questions as possible today. If you're not able to answer some of the questions today, we'll reach back to you in the upcoming days. And finally, please don't worry about taking notes. We will be sharing the slides and a webinar video link afterwards. Your next slide, please. All right, to get the ball rolling. As many of you know, GWatch is a technology company based in Norway with industry-leading expertise in microseismic monitoring and gravimetric monitoring. At GWatch, we have two key business units. On the right-hand side, we have the Octio business unit with two key product offerings. GWatch, which provides long-term microseismic passive monitoring for improving the injection rates, as well as our latest offering, Depthwatch, which is active seismic monitoring using drill bit as a source, both for drill bit positioning as well as look-ahead imaging. The focus for today is GWatch side of the business, which is on the left-hand side. And we have two key offerings. GWatch, which is 4D gravity measurement sensitive to mass changes within the reservoir, as well as the Depthwatch, which is basically dealing with the seafloor subsidence due to reservoir compaction. Combining these measurements provide a time-lapse idea on how the reservoir is behaving based on production and helps us to improve reservoir monitoring and management. And the key message here is this services provide similar value as 4D seismic at 10% or 1/10 of the cost. And next slide, please, John. All right, so now it's time to introduce our speakers for the day. And I'm pleased to introduce Jon Yvonne Lindgaard, Vice President Sales and Business Development at GWatch, and Martha Lien, our Senior Geophysics and one of the leading forces behind GWatch. Jon has extensive management experience within GWatch, has been one of the early members of the team, and has done multiple roles within the GWatch. And as his part of his latest role, he's helping to take this technology faster to the market. Jon, Martha, welcome to the webinar. Hope you guys are excited. I'm super pumped. So welcome.
Thank you very much, Rajan. Yeah, I think we are ready to start, and this is quite exciting for us. We have all, as Rajan mentioned, all needed to adapt, and we are getting now used to, the everyday life where we are standing here or sitting, talking into the screen, and doing these webinar things is something new and exciting for us. So we are really glad that you are here to share this experience with us. So I'm going to give you about 20-minute introduction to the gravitude technology. I'm going to focus on gravity and subsidence monitoring. I'm going to give you some introduction and principles of this technology. I'm going to show some field examples, some field applications from the past. Then I'm going to talk a little bit about subsidence monitoring, the technology we call Depthwatch. And at the end, I'm going to give just a couple of words about one of the incremental values from Depthwatch, namely using the Depthwatch technology to position ocean bottom nodes in the depth, before I draw some conclusions at the end. So, gravity. It is just for me as a geophysicist, it is quite amazing to think of that one of the fundamental principles of school, namely Newton's law of gravity, can be used in reservoir monitoring. And at the end of the day, this is kind of the fundamental understanding we need in order to take this to the reservoir management domain. And using this type of knowledge together with seismic, together with well data, you're actually able to manage the reservoirs and get enhanced production and more and efficient management of the field. The GWatch technology is actually consisting of two independent monitoring tools. One part is the gravity part, which is sensitive to mass changes within the reservoir. It can monitor fluid movement. It can map depletion of hydrocarbon, and it can distinguish between different driving mechanisms. Then we have the measurement of sea floor subsidence, which again is sensitive to reservoir compaction and can actually give us, together with the well data, we can actually utilize the map we get from seafloor subsidence to actually give quite a good estimate of pressure communication and pore compressibility in the field itself. I also need to mention that the seafloor subsidence is also a very important factor for us to correct the gravity measurements we are doing then, so that when we are correcting for the fact that the measurements are moving closer to the center of the Earth, the gravity time-lapse signals we are left with are actually representing only the mass changes and not the fact that we are moving closer to the center of the Earth. So there's a reason why these two data sets are collected together. So by using this type of monitoring, we are actually able to make a map of the subsurface away from areas where we have wells and more information. And this can give us quite a bit of information, for instance, on lateral compartments, as mentioned here. This is, as Rajan already mentioned, a cost-effective technology, and we can acquire data at a fraction of the cost of seismic surveys. So I'm going to just take a couple of minutes to talk to you about this technology and give you some kind of basics about it. So what we are seeing here, the white box here is what we call the sensor frame. In this sensor frame, that's mainly the instrumentation package we are using when we are acquiring these type of data. Inside this frame, we have 3 relative gravity meters and 3 pressure sensors. And these are mounted on a work-class ROV, as we are seeing here. And then we are going out with a vessel with this world-class ROV, and the ROV is carrying the sensor frame around to different predefined areas on the seabed, where we are doing measurement on these white things here, which we call concrete platforms. So the concrete platforms, it's basically just a platform consisting of concrete. It's about a meter in radius, so it's not a very big dish at all. So we are going down. We are doing measurement for some minutes on the concrete platform before we are leaving and moving on to the next one. We are actually, so the way the operation works is, before we start monitoring a field, we need to do some modeling. Where do we want to place these different concrete platforms? We are then deploying these concrete platforms on the seabed. These are both placed over the reservoir area, but also some of them are placed outside the reservoir area. And this way we are able to distinguish effects happening in the overburden and effects actually happening in the reservoir itself. And these are some quite important principles when we are doing the monitoring, in order to understand effects actually originating from the reservoir itself. These concrete platforms, they are placed at some distance from each other. As a rule of thumb, we are using the same concrete platform separation as the depth from the seabed down to the reservoir. So if there is 1 kilometer from the seabed and down to the reservoir, these concrete platforms are usually placed 1 kilometer away from each other. And this is allowing us to get a good understanding of the reservoir dynamics. So that was just a quick view of the operation. We will obviously get more back to this as we go. So one example of this in practice is, say that we have a gas field like this red area. So the gas field is being produced by a well, and before the production, we are going out when we are performing a gravity survey on these yellow concrete platforms, as you see on this picture. So then, after a couple of years, we have water from the surrounding aquifer that is starting to enter into the reservoir zone. Water has a higher density than gas, and this means that we are evolving a positive gravity change in the reservoir zone. So that means when we are coming back after a couple of years, we will be able to see positive changes in gravity on this station here. Maybe we are seeing some on this station here as well, but not as much, because you see that some parts of the affected area that will affect the measurement here is actually undrained. And this area to the very left is will see very limited changes. And that's one very basic example of how we can, for instance, detect undrained compartments, and also how we can actually measure the aquifer strength, and eventually also obtain an understanding of the hydrocarbon volumes in place. When it comes to subsidence, what we are doing is of course, again, going down, measuring the pressure on this water pressure on the seabed before the start of production. Then after some time, say that you are producing from a gas field again, and you are not experiencing the same support from the surrounding aquifers. This can introduce the reservoir to compact, and this will also allow the seabed to compact. And this will be an effect that we are able to monitor. So we are then able to obtain a map of lateral areas where we are experiencing subsidence, lateral areas of perhaps limited subsidence, and this may be areas of that has not been drained. This will allow us some quite important information about pressure development in the reservoir. It can give some quite nice constraints on the compressibility of the reservoir itself, and also the permeability. This type of information can then be used to better understand when it makes sense to perform drilling in the area, and it can also improve the geomechanical model of the overburden. So if you have some wells, you can calibrate the wells with the information you're getting from subsidence. You can basically get a quite good understanding of both what's happening inside the reservoir, but also in the overburden, which for some fields may be of interest. So without us getting into all the details, since this is an introductory webinar, I still want to show a few cases where this technology has been used. And as you can see immediately, this is a technology that has been around for some years. There's a big variety of the burial depth, so that means a distance from the seabed and down to the reservoir itself. You have, for instance, examples like the Depthwatch field, where you are at nearly 3,000 meters, and you have other areas like the Sleipner where you are at only 800 meters. So there's a bit of a difference in the different fields, and there's obviously also differences in the sizes of the monitoring area itself, from Mikkel of 21 concrete platforms to Ormelange, who has about 120. You can also see that there's different applications that has provided value for the monitoring itself, and we have tried to give them different colors. So blue is representing the color where the value comes from subsidence, and white is representing the colors where value comes from gravity. So it's a bit of a different thing from case to case. I also want to mention that this technology is many times used together with 4D seismic, but some cases it is actually used without 4D seismic at all. And we have some examples, like for instance the Mikke field and the Osterhandsteen field, where 4D gravity is actually the only 4D monitoring technology that is being used to manage the reservoir. So since many of you have quite a bit of, so just from university we'll learn about gravity, but not usually the same gravity as what we are talking about. So for instance, myself, I spent some years on seismic vessels. There we acquired the shipborne gravity, and I just wanted to show this slide here just to show the difference in the precision you can obtain from different types of method. So you can see that shipborne is, for instance, about 1,000 microgal, while the seabed seafloor subsidence, seafloor gravity signals we are able to obtain is in the range of 1 microgal. This technology has actually developed quite a bit since it was started in 1998 and throughout where we are today. And I would also like to mention that just within the last 4 years, we have actually improved the sensitivity of this technology with a factor of 5. So this allows us to actually see smaller changes in the reservoir itself. So at the end of the day, when you are measuring a specific observation in the field, you need that in order for this observation to be significant, you need it to be 2 times bigger than the uncertainty of the data you are having. So by reducing or actually improving the precision, we can actually see smaller things. And this is the reason why technology development in this domain is so important. And this is also the reason why in some places you can actually have a sub-meter resolution when talking about the gas-water contact. So now I'm gonna move on and show a couple of case studies that we have done in the past. Not in too much detail because this will be covered in the follow-up webinar, but I just wanted to give you some feeling about the results that are coming out from this type of survey. So this is coming from a publication in 2017 on the Ormen Lange. And from this paper and also from the status in 2017, subsidence is quite critical to understand the reservoir compaction, and it's actually not accurate enough to use 4D seismic time shifts for these type of analysis. Gravity is used for providing immediate insight to the mass balance in the field, and this is also integrated into a history matching workflow. And for me personally, what is really interesting about Ormen Lange is the way that 4D seismic and 4D gravity is actually used complementary. And one of the things that is quite interesting is that by using 4D gravity and subsidence monitoring on Ormen Lange, the operator is able to reduce the frequency of acquiring 4D seismic. So, of course, that meaning that there's a larger distance in time between each acquisition. And that is, of course, allowing a lot of cost savings at the same time as 4D gravity and subsidence is providing quite a bit of value when it comes down to understanding the status of the reservoir. We have also shown or given some feedback that they will be carried out a new data set in 2020. So that's something we are really excited to say something about that at the right time. So then I'm gonna show one example from Snowbit, and this data example here is actually extracted from a paper that was presented at the virtual SCG conference that took place, I guess it was last week. And it's focusing on the data acquired in 2019 and showing here some gravity changes between 2011 and 2019. And again, the way it works with these plots is that the blue circles here are indicating an area where you have a positive mass change in, and the red one is actually an area where there's a negative mass change over the reservoir for the given time period. And the results from the 2019 data is that there's quite a big impact using the 4D gravity data in together with the reservoir model. It's improving the model quality. There's also some quite nice qualitative examples of how we can understand the developments in the field itself. So one example is that there is actually a small fault in the area here where you have the arrow pointing, and the fact that we are observing a positive change in mass over this area here is actually indicating that there is communication over these faults, and that these areas here have actually experienced the water influx. So water has come in from the surrounding aquifer and taken place inside the area because the hydrocarbons has been produced and gone over to the producer. There's also quite a lot of information to be obtained by being able to constrain quite a lot of important reservoir parameters through history matching. And these ones are, for instance, related to relative permeability and porosity, communication between faults, and also initial hydrocarbon values, and of course water influx. So I think that's actually all I want to say about Snøhvit at this time. We will talk a little bit more about Snøhvit in the next round, but I hope you now just have a initial understanding of what type of information that can be obtained from this data. So with that, I actually want to show a couple of slides regarding Depthwatch. So Depthwatch is, of course, subsidence monitoring, as we mentioned. Here we are taking out, so in GWatch we are measuring both 4D gravity and subsidence. And in Depthwatch we are actually taking out the instrumentation belonging to only subsidence monitoring, and we are including it in a separate package. So this actually allows us to get the same type of resolution when it comes down to the 2 millimeter accuracy when we are monitoring subsidence. And we can obtain some quite interesting applications from this technology. For instance, reservoir compaction and understanding if there's compartments that are not producing, understanding what type of driving mechanisms are important for the given field, and quite a bit of interesting things related to geomechanics as well, as you can see in the list. Again, we are using the same principle where we are doing measurements over concrete platforms as shown in this picture here. And we are, of course, doing measurements both inside this area of expected subsidence, or areas inside the reservoir rim, if you like, and of course also areas that are outside, allowing us to get the understanding of the kind of normal conditions in the area. Yeah. What is interesting here is that when we perform the full GWatch technology, we need to use a world-class ROV. However, when we are acquiring Depthwatch datasets, we can actually use just an observation ROV. And the reason for that is shown on this picture on the right. It's very small and a very compact instrumentation that actually allows quite a bit of operational savings. So it's quite interesting technology that we have actually used a bit in the very recent times. I also want to mention another part when it comes down to incremental value from these technologies, and that's using the Depthwatch technology together with ocean bottom node acquisition. So one of the things you can do is actually to assemble the Depthwatch technology on a ROV that is used for placing ocean bottom nodes in the field itself. What that can provide for you is actually a very accurate understanding of the depth of the given node. This will be of very big value if you are operating at big water depths. like 2,000 to 3,000 meters, then you can actually obtain very accurate measurements that will not be able to come from normal ROV measurements, and this can be quite significant when it comes to the improvement on for instance 4D seismic repeatability and better understanding the multiples when you are using normal imaging methods. So we are actually able to get the node depths with less than 8 centimeter accuracy for a very low additional cost. The technology has already been demonstrated at actually 3 fields in the Gulf of Mexico. And the first results have actually been presented at the SCG 2019 by Shell. And I have included a reference to this paper below here. So by that, I want to just say a couple of words for conclusion, and it's that this type of technology can provide field-wide mapping and, of course, allowing for better and efficient reservoir management. We can map movements of fluid contacts, hydrocarbon depletion, and understand better the effects of aquifer influx and of course also drive mechanism. And using this data together with other data sets, for instance from wells, it's actually you can get some quite quantitative understanding of pore compressibilities, and you can also actually identify undrained compartments in the reservoir itself. This is data that is quite fit for incorporating into history matching workflows, and can give some both qualitatively and quantitative guidance into both the selection of key reservoir parameters and also in order to constrain different key parameters. So by that, I'm really glad that you all had time to join us this afternoon, and I'm really excited to hear some questions from you.
Thank you very much, Jan. That was a very interesting presentation. We have few questions in the chat and we'll go through them one by one. I would like to remind all the participants, if you have any questions, please type in the chat box and we'll go through them.